Chapter 3, we spent solving a single nonlinear equation f of x equals 0, and we studied several methods. Now we're going to look at a system of several equations. You should normally have the same number of equations as unknowns, whether your equations are linear or nonlinear or even differential equations. You normally want to have the same number of equations as unknowns. So we'll assume 2 equations and 2 unknowns, but it'll be obvious how to generalize it to larger systems. But Newton's method is the only one that really generalizes to systems, so let's review Newton's method from chapter 3 for solving f of x equals 0. What we did was we approximated f by its Taylor polynomial degree 1, otherwise known as the tangent line, at xn, where xn is the current best approximation. So that's f of xn plus f prime of xn times x minus xn, the first 2 terms of the Taylor series. And you set that to 0. That you can solve for x because that's just a linear equation. So you solve this for x and find the point where the Taylor polynomial is 0, and you hope that's closer to the point where f is 0. So solve for x, and you take f of x on the other side is minus of f of x divided by f prime, add the x in, and here's what you get. And that's Newton's method for a single equation. And we remember that Newton's method converges really fast if you start close to the root, and that will be the same with Newton's method for systems. So for our system of 2 equations, as I said, it'll be easy to see what to do with a system of 3 equations and 3 unknowns and so forth. But let's suppose we want to find a root of an x and y such that f and g are both 0. Well, you approximate f and g by their tangent plane, and this is the tangent plane to f at the point xn, yn. So you have a point xn, yn that's your best approximation so far, and you write down the tangent plane there. Well, this is the tangent plane. Why? Well, this is just a constant because it's f at a particular point. That's f sub x at a particular point, constant, constant. So everything's constant except this x and y, so it is a plane. And it has the same value as f because when x is xn and y is yn, these terms disappear and you get f of xn, yn. It has the same first derivative with respect to x because the derivative of this with respect to x is just the constant coefficient of x, that, which is the derivative of f. And similarly for f of y. So this is a plane, it's a linear function, has the same value, same x partial derivative, same y partial derivative. We do the same thing with g, expand it and write out its tangent plane. You set both tangent planes equal 0. In other words, you try to find the point xy where both tangent planes to f and g are 0. So solve these 2 equations for x and y. These are linear equations, so they're pretty easy to solve. You take the f and g on the other side, minus f g vector, and you have a matrix f sub x, f sub y, g sub x, g sub y. This matrix called the Jacobian matrix times the vector x minus xn comma y minus yn equals minus fg, and you multiply by the inverse and then take the x in yn. Anyway, that's a little, I'm going pretty fast here, but basically just solve this for x and y. And you say, well, that x and y hopefully is a better approximation because it's where the 2 tangent planes are both simultaneously 0. So hopefully it's close to the point where both the surfaces f and g are 0. So you can see that looks a whole lot like the Newton's method for a single equation. I wrote, normally we write this as f of xn over f prime of xn, but I wrote it as f prime to the minus 1 to make it look more like the systems. So basically the new vector is equal to old vector minus derivative inverse times the function. Function has 2 components, function's a vector. The derivative is a 2 by 2 matrix, a Jacobian matrix that consists of the partial derivative. First row is partial derivatives of f, second row is partial derivatives of g. And that means matrix inverse. So this is very similar in looking to the Newton's method for a single equation. Notice that all 6 of these functions, f, g, and the 4 partial derivatives, are all evaluated at the current best approximation xn, yn. And we'll see that this has some of the same properties as Newton's method for a single equation. For example, if your function happens to be a linear already, then Newton's method converges in a single iteration no matter where you start, because if your function f happens to be a straight line, you approximate it by its tangent line. That's Taylor polynomial degree 1. It's exact approximation, so the root of that is the root of f. Same thing in a system. If both of these functions are linear, then you're approximating them both by their tangent planes, which will be exact, and the root where both tangent planes are 0 is going to be exactly the point where f and g are both 0, because tangent planes are f and g. So it'll converge in a single iteration starting anywhere if f and g are linear. Now, of course, you might say I wouldn't bother using Newton's method if they're linear. I just solve for x and y. But there are times when you don't know whether it's going to be linear or not, and if it happens to be linear, that works just fine. So much the better. It converges fast. Just assume it's nonlinear. Use Newton's method. Converges quickly if it's linear. And it also, we'll see, has the property that if you start close to the root, it'll converge really fast, quadratically again. If you start far away from the root, then lots of things can happen, mostly bad. Another thing to notice, one of the main disadvantages of Newton's method is you need to know the derivative of f. Well, for a system, that's an even worse problem. Suppose you had a 100 by 100 nonlinear system, then you've got a 100 by 100 matrix, 10,000 partial derivatives to calculate. You don't want to calculate those by hand. So most programs that use Newton's method to solve systems will give you the option of where you don't have to actually supply all those partial derivatives yourself. It will approximate them using finite differences, basically like section 5.4. It'll approximate f sub x by f at xn plus h comma yn minus f of xn comma yn divided by h. Use a finite difference approximation, and then as in section 5.4, we have to be careful not to choose h to be too small, because if you choose it to be small, you can get serious round-off error problems. So you want it small enough so that its truncation error is small, but not so small that the round-off error is real small. Fortunately, with Newton's method, if you have a bad approximation to the Jacobian, it won't make it converge to the wrong answer. At worst, it'll make it converge slowly or not converge at all, but as long as you supply f and g correctly, it won't converge to the wrong. It won't converge to a point where they're not 0. So you've got a little bit of leeway in calculating these partial derivatives. They don't have to be exact. But if you can, 2 by 2, you might want to actually supply the 4 partial derivatives. By the way, since Calculus 3 is not a prerequisite for this course, some of you may not even know what partial derivatives are. So when we go through examples, we'll remind you what partial derivatives are. If you can take ordinary derivatives, you can take partial derivatives, because f sub x is simply the derivative of f, considering that x is a variable and y and any other variables are just constant. So there's really nothing to it except remembering that the other variables are considered constant. Okay, let's do an example now. Here's a MATLAB program to solve the system of two equations. The first equation is x squared plus y squared equals 1. Second one, x squared minus y squared equals minus 0.5. We have to take everything on one side because Newton's method assumes that f and g are the functions that are equal to 0. So turns out that one of the roots is x equals 0.5, y equals square root of 3 over 2. And here's the Jacobian matrix, partial of f, this is f and that's g, or f1 and f2. Partial of f1 with respect to x is 2x. Partial of f1 with respect to y is 2y. Remember, you're taking the derivative with respect to y, considering x to be a constant. So derivative of constant is 0. Derivative of y squared is 2y. Then the second row is the derivatives with respect to x and y of the second function. Derivative of the second function with respect to the first variable x is 2x, and then derivative y squared is 0. Then when you direct the derivative with respect to y, that's 0 and that's minus 2y. So there's the Jacobian matrix. And then xn is a vector. That's the two-component vector. The new xn is old xn minus j backslash f. That means basically J inverse F. So that's all done automatically for you, and then we're calculating the error just so you can see how fast it converges. We happen to know the true root here. We start at 1, 1 for lack of a better idea, and so let's run it now. And it converges very fast. Quadratically it looks like, because after, I don't know, 3 iterations the error is 10 to the minus 4. After 1 more iteration it's 10 to the minus 8, and then 10 to the minus 16. It's already down to round off error, so it looks like super fast convergent, just like it does with a single equation. It's converging to 0.5 comma square root of 3 over 2, which is this, so everything's working fine. Now notice that that's just one root. Notice that x and y only appear squared, so that means if you change x to minus x or y to minus y, it'll still be a solution. So you take any point xy which makes both of these 0 and change the sign of either x or y. In other words, there's at least four roots here. We found one of them, but you can, plus or minus 0.5 plus or minus square root of 3 over 2 should be roots. So let's see what happens if we start at 1 comma minus 1. So I'm going to start from 1 minus 1, and I suspect that's going to converge to the root at 0.5 minus square root of 3 over 2. So I've changed the true solution to that so we can compare. And let's see. And sure enough, it does converge to the other root in the fourth quadrant. So there's 4 roots. It looks like you start close to any one of the 4, it'll probably converge to that one. There may be some values of x and y for which it goes off to infinity, but at least if you start close to one of the roots, it should converge to it, and it converges quite fast.